Thank you. So my plan of these 3 lectures, which you sort of see outlined here, is to begin by telling you about sparsification of graphs and matrices. So sparsification of a graph is the approximation of a graph by a sparse graph, where by sparse I mean having few edges. I'll explain exactly what this means later in the lecture, but one of the key points is it turned out, when we started thinking about this problem, we thought it was a problem in graph theory. But it turns out that at least our solution of it has nothing to do with graphs. It's really a statement about matrices, which is why this will really be about sparsification of matrices. The next 2 lectures will be about the solution of the Cadison-Singer problem, which is going to be closely related to the material I will present today, at least in appearance. So when I present a theorem about sparsification of matrices, if you just changed a few characters, it would prove the Cadison-Singer problem. Unfortunately, removing those few characters took 5 years, but at least I will, in this first lecture, explain to you some of the techniques that will come up in the solution of the Cadison-Singer problem. And I will tell you about Ramanujan graphs in the 3rd lecture and show you a new proof that there exist the first proof that there exist Ramanujan graphs of every degree. Part of my goal in today's lecture is to really explain what these 2 things should have to do with each other, because it's not at all a priori clear that Ramanujan graphs have anything to do with the Cadison-Singer problem. And formally they don't, but in terms of techniques, there's a lot in common in thinking about them. So while, for people who aren't here today, you can tell your friends that I intend these lectures to be self-contained. But my goal in today's lecture is going to be at least getting you used to the sort of techniques that I'll use in the other lectures. So sparsification of graphs and matrices is about joint work I did with Shang-Hua Teng and Josh Batson and Nikhil Srivastava. So my toy example that I give you here is this is the complete graph on 10 vertices. And let's say I wanted to approximate it by a graph having many fewer edges. I will use the famous Peterson graph is the best sparse approximation I know of it. And one thing you will note in my picture is here I drew the edges thicker. There's a reason. I really mean they should be thicker. My notion of sparsification will correspond to getting rid of some of the edges. But then if I'm going to get rid of some of the edges, there's going to be some sort of notion of conservation of mass. So if I get rid of some others, I'm going to have to make others thicker and with heavier weight. But this is just the cartoon. So let me explain what I really want to do. OK, so Shang-Hua Teng and I proposed this problem of spectral sparsification, which is a problem taking an arbitrary graph and approximating it by a graph with few edges. Actually, there are many different ways of defining what it would mean to approximate a graph. We're going to look at a graph in terms of its Laplacian quadratic form. So to fix notation, for me, a graph will always have a vertex set V, an edge set E. And I look at graphs with weights on edges. The weights should be non-negative. Really, they should be positive. So W is just something that assigns a weight to every edge. OK, so graphs for me are isomorphic to what I call Laplacian quadratic forms. These are, well, they take as input a function x on the vertices. So x assigns every vertex a real number. And then the value of the quadratic form at x is the sum over all edges of the square of the difference of x across the edges times the weight of an edge. When you have a quadratic form like that, you can always write it as multiplying a vector by either side of a matrix. That is the matrix. It's called the Laplacian matrix. I might show you what the Laplacian matrix is later in the talk, but it's not as important to me what the entries look like. I really just care about the quadratic form. OK, I'm giving you the abstract definition. First, let's do a concrete example or 2 to get used to the Laplacian. Here's a very simple graph. Imagine that all of my edges have weight 1. And now I've drawn my function x on the vertices as well. So x has 0 on these vertices and 1 on those 3 vertices. If I now want to compute the Laplacian quadratic form, I sum over all edges of the difference of x across the edges, which, I think I should do on this slide. So edges going from 0 to 0 have no contribution. Edges going from a 1 to a 1 have no contribution. The difference is 0. Actually, the only edge that contributes to the Laplacian quadratic form here is the edge going from a vertex labeled 0 to a vertex labeled 1. So on this particular x, the value of the Laplacian quadratic form is 1. This is, to me, a very interesting sort of vector x in having values 0 and 1 at the vertices. In general, if I have a subset of the vertices, let's call it S, I can look at the characteristic vector of S. Say it's the vector that's 1 at the vertices in S and 0 outside. Well, then what happens is the Laplacian quadratic form will get a contribution for every single edge going from inside the set S to outside, and the others won't contribute. So I haven't drawn here the edges that don't contribute. And the value of the Laplacian quadratic form would either be the number of those edges if they were all at weight 1, or if they have weights on them, it is the sum of the weights of the edges. Okay, so this is an example that is very important to me, because when I am looking at graphs, I'm also often interested in understanding for various sets of vertices how big is their boundary. Sometimes I'm trying to show that all sets have high boundary. That will be like Ramanujan graphs. Or sometimes I want to partition a graph. Then I want to find sets of vertices with small boundary. But measuring boundary is, to me, a very useful thing to do. And then it's useful that the Laplacian quadratic form gives us a way to do this, or at least when we plug in characteristic vectors. Okay, that is a very brief introduction to the Laplacian. I give entire lectures or more on the Laplacian. I know some of you have seen them, some of you haven't. I should just stop for questions if there's any question about what it is that I'm defining right now, because this is what the whole talk is going to be about. Okay. If you later decide you have a question, don't hesitate to stop me. We have a board. We can go back. It's okay. So I should tell you at least a little bit about how you assemble these Laplacian matrices. So when you take a look at this Laplacian quadratic form, it's useful to me to observe that there is a term for every single edge, which means we can write the Laplacian matrix as a sum of elementary Laplacian matrices, one for each edge. So between vertices u and v, I will make a Laplacian which just corresponds to edge uv. And here's what that looks like. Say if I just have two vertices, let's label them 1 and 2, the matrix, the Laplacian matrix looks like this for the edges just between, or an edge just between vertices 1 and 2. If there were more vertices in my graph, then just pad out with zeros. For me, the important thing about this matrix is that it's rank 1 and it's an outer product of this vector with itself. And in general, for LUV, that's what will happen. LUV is the outer product of a vector with itself, and it's a vector that's 1, I'll call it BUV. It's 1 at one of the vertices and -1 at the other. Which one has the 1 and which has the -1 doesn't matter, because you're taking the outer product with itself. So the signs disappear when you multiply. Okay, so to me, this is really going to be one of the most important properties about Laplacians, that we can write them as a sum of outer products. This tells us many things about the Laplacian. First, as a matrix, it's positive semi-definite. That just means all of the eigenvalues are non-negative. And that just follows because this quadratic form is never negative when we plug in real numbers. Also, if the underlying graph is connected, this tells us that there is one eigenvector of eigenvalue 0. It corresponds to any constant vector. And that is exactly the null space. The constant vector is always in the null space. But if your graph is connected, only the constant vector is in the null space. I want to say right now that I know what the null space is, and I will usually ignore it. Meaning, you may catch me talking about the inverse of the Laplacian. I mean, formally, it doesn't have an inverse. It's singular. I'll mean the pseudo-inverse. Well, if I ever say that, I mean work orthogonal to the null space. And everything will be fine. OK, I've told you a little about the Laplacian. Now I can tell you what it will mean to me for one graph to approximate another. Or more importantly, what it will mean for their Laplacians to approximate one another. We'll start with the definition for matrices, borrowing notation, which I first learned at least in optimization, where people will say that one matrix, say M, is less than or equal to another matrix M tilde, if the quadratic form in M is always less than or equal to the quadratic form in M tilde for all vectors. This is equivalent to saying, some of you will be familiar with the fact that M tilde minus M is positive semi-definite, or sometimes called the Loevner partial order on matrices. OK, so this is a notion of what it means for one matrix to be less than or equal to another. I'm going to overload this notation and extend it to graphs. So I'll just say one graph is less than or equal to another if the corresponding Laplacian matrices satisfy the same inequality. OK, now that we have a notion of less than or equal to, we can start to get a notion of approximation. So first I want to point out you can also talk about multiplying by k. Here you can put, a constant times one of these matrices. And you can ask, when I might say that a graph G is less than or equal to k times a graph H. Well, that's the same as if the Laplacian of G is less than or equal to k times the Laplacian of H. And you can interpret that almost any way you want, and you get the same answer. In other words, when I talk about k times the matrix, you could think about multiplying every weight by k. That is the same thing as taking k times the Laplacian matrix. Okay, so we will now say that one matrix M is an epsilon approximation of a matrix M tilde. If it should be that the Laplacian quadratic forms in M and M tilde are very, very close. Meaning, for example, say that M tilde is less than or equal to 1 plus epsilon times M, and is at least 1 over 1 plus epsilon times M. By the way, the dimension doesn't come in. This will be a dimension. Oh, so yes, you should. This definition will make sense for any epsilon. Later in the lecture, I will do this for epsilon equal to 2.6, so that won't be very small. But usually we care about epsilon small, like a tenth or something. Oh, sure. Independent of the dimension. Yes, it's a notion that's independent of the dimension. This really just says that the value of the quadratic form in M tilde is always less than or equal to 1 plus epsilon for every vector, the value of the quadratic form in M. And you might be wondering, why did I choose to write 1 over 1 plus epsilon here instead of like 1 minus epsilon, which is my first instinct? This is the definition that makes the notation symmetric. So I want M to be, I want to be able to reverse the roles and have the same definition. This is the right way to do it. OK, and then I can overload this notation and extend it to graphs. And just to emphasize, this literally means that for every single vector you plug in, the ratio of the quadratic forms should be between 1 over 1 plus epsilon and 1 plus epsilon. So it's a very strong notion of approximation. In particular, if I have two graphs, and G is an epsilon approximation of H, well, then their Laplacian matrices have similar eigenvalues. All the eigenvalues can be paired up within a 1 plus epsilon factor. If eigenvalues are isolated from each other, it means the corresponding eigenvectors are similar, have small angle to each other. It means, in particular, the boundaries of every set in the two graphs is the same. So if one set graph is an epsilon approximation of another, for every set of vertices, at least the sum of the weights of edges in the boundary of that set has to be similar. To me, actually, the reason I was looking at this notion is it means this is how I write the pseudo-inverse. The pseudo-inverse of G is approximately the same as the pseudo-inverse of H. And they're epsilon approximations of each other. I cared about this because Shang-Hua, Teng, and I were first studying this in designing algorithms for solving systems of linear equations in Laplacian matrices. And when one matrix is an epsilon approximation of another, it means that the solution to systems of linear equations in one Laplacian matrix is similar to the solution of systems of linear equations in the other. Or if you do numerical linear algebra, it means one can be used as a preconditioner to solve systems of linear equations in the other. But that is not what this talk was about today, but it was the entire motivation behind doing this at first. OK, so Shang-Hua, Teng, and I asked the question of, for every graph, can we find a good sparse approximation of it? So if you give me any graph G with n vertices, can we find a sparse graph having, OK, by O tilde of n, I mean something like n times log n or n times the power of log n. But can you find a graph where the number of edges looks asymptotically like n that's a good approximation? We need to do this for every graph. And in our first paper on this, we showed that you can, although it was really like n times log n to some high power of log n, like 8 or 9 or something. But in our first paper on this, I showed we did it, and we used very special properties of graphs in order to prove that something like this existed. Today, I will give you a graph-free proof. So we're really going to see that trying to do this really is a statement that's much more general about, or at least you can do it using much more general techniques in elementary linear algebra. We were using, OK, so there was some random matrix theory, random sampling type things. Yeah, so what we're using about graphs. We were using facts about partitions of graphs. In particular, we're using Cheeger's inequality in a very powerful way. And that really that's a graph thing. I should mention later that I have some conjectures I'll mention in this talk, which you might miss at the very end, which seem like they might be special to graphs and not linear algebraic. But I really do not understand well what graphs give you for this problem yet. But I do know a few things you'll see, or if there's time I can mention it. You know how to do for graphs, we don't know how to do in general. Yes?
So when you have all the edges, that doesn't mean you kept the weights the same.
No. Yeah, we will take, yeah, we have not, you can't keep the weights the same, as a matter of fact. Yeah, so when you drop edges, you have to scale up weights. Okay, so you can ask why, oh, yes. Oh, the tilde here really means n times some power of log n. So the first order terms, we go of n. But we're going to get rid of all of that later. It's going to become a 4 over epsilon squared later. So, okay, so you can ask, why would we think we can do this? Well, the first question you can ask yourself is, what about the complete graph? Can you get an approximation like this for the complete graph? I mean, take the graph with every possible edge and give it weight 1. And you can, and the reason you can is because expander graphs are the right sparse approximations of the complete graph. Okay, I should do a survey. The results might be embarrassing. How many of you here, can I get a show of hands, know about expander graphs? Good. Well, almost everyone. Still not as many as should. So, okay, so usually when we think about expander graphs, these are graphs where we're going to keep the degree of every vertex fixed. We'll call it d. And imagine letting n grow, the number of vertices. And expander graphs, they act a lot like random graphs like this. One thing we do know is every set of vertices has very large boundary, where large is, in your best expander graphs, as big as you could hope it will be, given the size of your set of vertices. You know, the bigger the vertices, the smaller the boundary tends to be. Sorry, smaller as a fraction of the set of vertices. These are the graphs where, say, random walks mix very quickly. And I should also mention that, at least as a theoretical computer scientist, they are incredibly useful. There are the number of theorems in theoretical computer science, the number of important theorems in theoretical computer science that depend on expander graphs really cannot be counted. They make their way in everywhere. So this is something that I've had to learn a lot about. So, but OK, this is not a precise mathematical definition. Why don't we get a little more precise? So let's look. One way of characterizing expander graphs is by looking at the eigenvalues of their Laplacian matrix. And at first, OK, back when we first had expanders, we defined them as graphs where all the eigenvalues were bounded away from 0. You know 0 will always be an eigenvalue of the Laplacian. You want some constant which all the eigenvalues are bigger than, at least as n grows. You want them all to stay bigger than that. I now call those weak expanders because we can do better. But you know, back in the 80s, early 80s, we were happy with that. Then we got graphs which I'll call strong expanders. Here, all of the eigenvalues of the Laplacian, other than 0, are approximately equal to the degree. So all the eigenvalues are very concentrated around the degree. So let's see why strong expanders give you a good approximation of the complete graph. So if G is the complete graph on n vertices, it turns out all of its non-zero eigenvalues are just n, the number of vertices. So it's really like an identity. What this means is if I put in any vector x orthogonal to the 1's vector, say if x is a unit vector, then the value of the quadratic form on that x will be n. On the other hand, for a good, strong expander graph, all of the non-zero eigenvalues are close to d. That means that the value of the quadratic form on every unit vector that's orthogonal to the all 1's vector will be approximately d. OK, d is not approximately n. I'm thinking of n as big and d is fixed, but that just means you need to reweight. So just multiply the weight of every edge by n over d. And then your expander gives you a very good approximation of the complete graph. OK, you can ask, how good can you get? Well, the best we know are the Ramanujan expanders, constructed independently by Margulis and Lubatsky, Phillips, and Sarnak. All of their non-zero eigenvalues lie between d plus or minus 2 root d minus 1. So at least for d big, 10 or 20, this is really a number that's very close to d. And by a bound usually attributed to Alon and Bapana, you cannot do asymptotically better. Meaning if n grows large and d is fixed, right, you can't move these numbers on either away by any constant. Your eigenvalues will always approach this. OK, so for the complete graph, We know exactly how good the approximations can be, and Ramanujan graphs give them to us. OK, so these constructions only exist for some special degrees, and in my third lecture, I will tell you, at least prove to you that they exist for all degrees. So that'll be the point of the third lecture. But at least from this, we've known that these things exist for a fairly dense set of degrees. Oh, I should have said the relation is exactly, or almost exactly the same. When you have the complete graph, if you're approximating the spectrum well, then you have exactly the right sort of approximation. Otherwise, it changes a bit. Because, right, if you have big and small eigenvalues, you've got to be small on the small eigenvalues and big on the big eigenvalues. The great thing about the complete graph is just all the non-zero eigenvalues are the same, so we don't have to worry. OK, so one of the questions we'd like to know is, can we approximate every graph this well? Does every graph have a sparse approximation that is as good as the Ramanujan graphs approximate the complete graphs? I don't know yet, but I will get you within a factor of 2. So that will, at least in terms of the number of edges, to get that quality of approximation. And to do better, I do believe you're going to have to use something special about graphs. No, yeah, I don't. Oh, sorry, I don't know any enemy. I think you probably can. That is my guess. I think you probably can approximate every graph this well. What is my enemy is that the tools that I am using from linear algebra are, you need more than that. You really need something about graphs to do this. So some of the theorems I'll show you later that will prove for approximation of matrices are sharp. You cannot improve them. But if you go to graphs, there's a lot special about graphs, as we'll see. Yes. Yes, we allow weights on the edges. And there are some very good, right, we'll allow you to put any weights you want on the edges. OK, so here's the main theorem, or one of the ways of stating it that I'll prove for graphs, or I'll sketch the proof of it for you today. It is for every graph G, there is another weighted graph H. I didn't say it, but the edges will be a subset of the edges, and we'll just increase their weights. So that G is an epsilon approximation of H, and the number of edges in H will be at most the number of vertices, so call that n, times this number, which will be, say, 2 plus epsilon squared over epsilon squared. If you think about epsilon being small, think of this as 4 over epsilon squared.
Oh, so the statement
Yes.
is that for every G and for every epsilon?
For every G and every epsilon, yes. Oh, yeah, I didn't even bother to say that. But yes, for every epsilon. It's uniformly true. There's nothing hidden here. And it's not probably immediately clear unless you're incredibly fast at calculating in your head. But for small epsilon, the Ramanujan graphs would do something similar, except this would be divided by 2. Yes, I will give you a polynomial time algorithm that is not particularly fast. Although I know that there's some people who are working on getting it down to about quadratic time. That's still slow. If we were willing to substitute and put in but we can get it in nearly linear time if you're willing to put a log n here. And the young kids keep coming up with faster algorithms every day. I know if I should call them young kids. Some of them are just newly minted professors. But we are getting faster algorithms all the time for this. So we'll see. OK, so we'll get within a factor of 2 of the Ramanujan bound. So as I told you, it's not going to be about graphs. So let me tell you why this is really going to be a theorem about matrices. We're going to look at taking a matrix M that I can write as an outer product of some matrix B with itself. Think of B as collecting all of those elementary vectors I had, one for every edge, in its columns. So think of this matrix. I drew it here to have more columns than rows. That's the right way to think of it. We want to take a matrix M like that and approximate it by matrix M tilde, where I subsample the columns, and I have the same columns here. So I want to downsample B and approximate it and get an epsilon approximation. And as I told you before, in order to do this, I'm going to have to scale up the columns I do keep. So this would be a better picture. You take some of the columns and blow them up. The way I'm going to think about this is I'm going to think about writing M as a sum of outer products. My approximation I'll also write as a sum of outer products with scaling factors in front. And just the key point is most of my scaling factors will be 0, and some will be big. But this is what we're going to do. So I'm going to show whenever you have a matrix M like this, or sum of outer products, we can always approximate it by sparse sum of outer products, where the number of terms will be non-zero will depend on the dimension. And our main theorem is that whenever we have a sum of outer products, we can always approximate it like this. So we get an approximation, and at most, the same number I gave you before of the scaling factors will be non-zero. So think of it as most of the scaling factors are 0, and then some other edges we have to scale up. Now, we're going to simplify this problem quite a bit by turning it into something that looks a lot like approximating the complete graph. When I tell you something like m tilde is an epsilon approximation of m, I can take these inequalities and multiply by the square root of m inverse on either side. And it turns out this is the same thing as approximating the identity by this term in the middle, which is slightly complicated. This is m tilde, and saying that m tilde times m to the minus 1/2 on either side approximates the identity. But this normalization makes our life much easier. So that's how we will translate the problem. What that corresponds to doing is for every single vector, it means I'm multiplying the vector by the square root of m inverse. And now my collection of vectors that I'm dealing with, my sum of outer products, is very special. I now have a set of vectors such that the sum of their outer products is the identity. There will be more of them than the dimension. This is what people often call a decomposition of the identity. People have many ways of thinking about it. A lot of people like to think of it as if you give me any vector u, the sum of the squares of the outer product of u with the vectors in your set is the norm of u squared. So you can think of it like as generalization of an orthonormal basis. OK, so here's our goal. After this normalization, our problem is just to find scaling factors. Most of them are 0, so that now the sum of my outer products times the scaling factors approximates the identity. OK, now these scaling factors, you'll see I am very hung up on. The reason is that they come up in a mysterious way in my proof. I'll explain to you exactly where they come up. And if we didn't have them, we would have proved the Cadison-Singer theorem with this result. So in some sense, it'll be clear in my lecture on Wednesday, but the Cadison-Singer problem is essentially equivalent to proving a statement like this, where all of the non-zero scaling factors should be the same, as long as there are no vectors of particularly large norms. So one exceptional case you have to get rid of. I'm not going to do that today. These scaling factors will come up in my proof for reasons that I do not completely understand. Yes? Oh, well, most of these should actually just be 0, is the way. Yes, yes, I want most of them to be 0. Or you can think of it as summing over some of the indices. So, yes? That's an interesting question. If you look at the proof I'm going to do today, even if you started out with a complete graph, it will not be clear that all of the SEs can be the same, that are non-zero. Yeah, right. But given what you know. Given what I know now, yes, if you gave me any edge transitive graph, then we could get all the SEs the same. But more importantly, there is a natural scaling of these. Once you've scaled them to this way, which sort of, so the scaling that I did sort of changes the norms of the vectors after you've scaled them this way. Yeah, we now know by what I'll talk about on Wednesday, that if none of these vectors had large norm, then all of these scaling terms can be the same of the non-zero terms. Yes, somewhat. Somewhat. It's a long and convoluted story, and that could be an hour in itself. And I'll tell you more about the proof on Wednesday. But, OK. I think it's Wednesday, I'm told. OK, good. If it, OK. I mean, I could give the lecture either day, but I'm prepared for Wednesday. OK. So what I'm going to do is I'm now going to give you an outline of this proof, and it's going to be algorithmic. So we're going to build this set of non-zero vectors, the vectors for which get non-zero scaling one by one. I'm going to do it iteratively. So we're going to start out with no vectors. And then I'm going to do a greedy algorithm. I'm going to pick a vector. And I'm going to say, OK, that's going to get a non-zero scaling factor, and I'll set its scaling factor. And then I'll pick the next vector and set its scaling factor, and so on. So I'll do it one by one. so to do this, we need to understand what happens to eigenvalues of matrices when we add a vector. So in particular, let's just understand this pictorially. Let's say I start out with a symmetric matrix A, and here I'm going to draw the real line, and imagine these are its eigenvalues. Now what happens when I add the outer product of a vector with itself to A? It's a phenomenon many of us know called interlacing. The eigenvalues move forwards, and here I sort of drawn the ghosts of the old eigenvalues, and the new eigenvalues will interlace them. And they always do that. So this is a qualitative understanding of what happens when I add an outer product. Eigenvectors get bigger, but none can move past the previous ones that were there before. We need a more quantitative understanding, so we will look at the characteristic polynomial and see exactly how the characteristic polynomial changes when we do a rank 1 update. This is easier than looking directly at the eigenvalues. So if we look at the determinant of x times the identity minus a, what the rank 1 update formula for determinants tells us is that, and I look at the new characteristic polynomial, you can write it as the old one times a term, which is, well, 1, plus a sum, and the terms in the sum, they have an x in the bottom, so it's 1 over an eigenvalue minus x, and sort of the amount by which this changes depends on the inner product. If ui is the eigenvector corresponding to the ith eigenvalue, the amount of change will depend on the square of this. Okay, I'm going to simplify this formula for our purposes in some sense. So the actual particulars won't matter, other than I guess I may as well mention this is sort of a classic fact about determinants, what happens to the determinant when I add a matrix. So in our case, it's going to be easier because our vectors are a decomposition of the identity. So what that means is if I take a look at any eigenvector, which I'm assuming ui, and I look at the expected square of the inner product of that eigenvector with a random vector ve from my set, because they're a decomposition of the identity, that will be 1 over m, where m is the number of vectors in my set. So what this means is an expectation. I can understand what happens to the characteristic polynomial when I add a random vector that's a decomposition of the identity. If I take a random vector and I add it to A, what happens is all of the terms up top here, at least in expectation, work out nicely. And I get that the way the characteristic polynomial updates is I take the old characteristic polynomial and subtract off 1 over m times its derivative. Because this is very nice. If I have a matrix and I know its characteristic polynomial, I can compute the expected characteristic polynomial that you get when you add to it the outer product of a vector with itself when those vectors are from a decomposition of the identity. And then I can understand what happens when I do it many times. If I add k vectors at random from my set, it's just like applying this same operator k times. And we'll start out with no vectors. So in that case, it's like I apply this operator k times to the characteristic polynomial of the empty matrix, which is x to the n. So now in expectation, I can understand what happens. In expectation, the expected characteristic polynomial I get if I take k of my vectors and I add their outer products together is, well, this is actually an associated Laguerre polynomial. Actually, I should have asked for a show of hands of how many people knew what this polynomial was. It's not the way associated Laguerre polynomials are usually written, but they're one of the classic families of polynomials. And we know pretty much everything you could want to know about their roots. In particular, if I take an associated Laguerre polynomial like this, where k is some multiple of n, so n over epsilon squared, we know that the roots of the corresponding associated Laguerre polynomial are, up to a scaling factor k over m. They're basically like between 1 minus epsilon squared and the square of 1 plus epsilon. The important point is the ratio of these two terms grows small as epsilon grows small. So associated Laguerre polynomials, as you go out far enough, all of the roots compact together very nicely. And this was the inspiration for our analysis. There's only one problem with using what I've told you for our analysis so far. So I've told you something about the expected characteristic polynomial. And unfortunately, in general, that doesn't buy you anything. So usually, if I tell you about the expected characteristic polynomial and its roots, that usually has nothing to do with the roots of the actual polynomials that are in that expectation. So just because the expected polynomial has roots exactly meeting the bounds that I want, it doesn't mean that there's any particular realization or choice of vectors that does. I say in general and usually here, and I'm hedging, because in my next two talks are all based upon the fact that if you have the right family of polynomials, actually there is a clean relation. And that's what we're going to exploit in the next talks. So for very, very special families of polynomials, the expected characteristic polynomials tell you a lot. But actually today and for today's lecture, they don't. So I can't just look at the expected characteristic polynomial to say, there is a good approximation. But this at least will guide our analysis. And I will still show you there is a particular choice of vectors you can add that will satisfy these bounds precisely, or at least as good. OK, so now that I've given you the motivation, I can tell you, or for the proof, I can tell you actually how we make it work. So I'm going to put in some particular numbers to help illustrate. So if my vectors live in n dimensions, I will form a collection of 6n of them. And after scaling, all the eigenvalues will lie between 1 and 13. And that will get me a value of epsilon being 2.6, where I think it was like 2.6 plus 1 squared was 13, I think was where that came from. It's approximately 2.6. So here's the idea behind the argument. Again, I want to corral the eigenvalues. So the way I think about it is I start out with the empty matrix where all the eigenvalues are 0. And I've got a barrier keeping the eigenvalues on either side. I'll start with my barriers at n and minus n, where that's the dimension. What happens at every step is I add an outer product. Some eigenvalue is going to shake loose and move forwards. And I'll move my barriers forwards. And what I will do is on the lower barrier, I'll be conservative. I won't move it very far. My upper barrier will be a little aggressive. It will move further. And the idea is that on average, at every step, my eigenvalues will move forwards 1. Or sorry, an eigenvalue will move forward 1. And my barriers, actually on average. And my barriers will move forward, the lower one less and the upper one more. So the idea is that if I keep doing this, moving the lower barrier forward 1/3, I think, in the upper barrier 2, after 6n steps, my lower barrier will have gone from, minus n to n. My upper barrier will have gone from n to 13n. OK, so all my eigenvalues will be between n and 13n. That's what I would want. And if we could do that, we'd be done. Then we would have this 2.6 approximation with 6n vectors. OK, here's the problem. OK, this is just a cartoon. How do we make it work? I need to prove that at every step there is a vector in my set that I can add. So I need to show there is an outer product I can add. And the other problem is just assuming that the eigenvalues lie between these barriers. That is not a sufficient assumption for induction. I want to do an inductive argument, and that is not a strong enough inductive hypothesis. And the reason sort of goes back to interlacing. If I have a bunch of small eigenvalues, after a step, one of them is still going to be small. It's not going to move past the next, no matter where my lower barrier is. So there's a problem. If there are a bunch of eigenvalues bunched up and my lower barrier is here, I can't move them there. And also, eigenvalues have this repulsion property, which I can explain in more detail sometime if people want me to. But if you have a bunch of large eigenvalues bunched up, then the highest one is going to tend to shoot off far. So again, my upper barrier, like my largest eigenvalue, wants to shoot off far, and I only want to move my upper barrier a little bit. OK, so we need a stronger inductive hypothesis. What we're going to do is we're going to introduce a way of measuring how close the eigenvalues are to the barriers. That will be the key. And the way we're going to do it is by what we call this, well, first I'll start with what we call the lower barrier potential function. This will be a measure of how close the eigenvalues are to the lower barrier at L. And what we do is we sum 1 over the eigenvalues minus L. So what this picture is it's telling you that here is the, if I have an eigenvector here, the height of this is the weight we will assign to it. And it blows up as you go towards L. it will be very important to us that this is also the trace of A minus L times the identity inverse. Some of you, actually, get a show of hands for how many of you recognize this? Okay, and then how many of you call it, okay, not many. This goes by 3 different names I've encountered. Either the Stieltjes transform, usually when it's used in random matrix theory, or the Hilbert transform or the Cauchy transform. I don't know why those names are used, but I've seen all 3. Okay, I'm sorry I've added a 4th. But this is going to be, it's a very useful thing. So when we measure this boundary, this tells us a lot. For example, if I tell you that the barrier function is less than 1, it means that all of the eigenvalues are at least 1 away from L, because if I'm 1 here, then the height of this is 1. But it tells us more than that. It tells you things like no 2 eigenvalues are within distance 2 of the boundary. No 3 eigenvalues are within distance 3 of the boundary, and so on. We also corral the upper barriers with an upper barrier potential function. It's the same thing, just the sum of 1 over u minus the eigenvalues. We will use this to measure how close the eigenvalues are to the upper boundary. Okay, so here's our goal now. I start with nothing, but now what I do is I look at the barrier functions. And with my barriers at minus n and n, where n is the dimension, my initial values of the barrier functions, the lower barrier and upper barrier, are both 1. Because I put in the trace of, say, n times the identity inverse, and it's an n dimension, so we count n times 1 over n. We are going to maintain that throughout the course of the algorithm, which is really an algorithm for constructing this matrix. So at every single step, what we want is that the upper barrier and the lower barrier are both less than or equal to 1. So this means that not only are the eigenvalues between the barriers, but they're not too close. And we will maintain that at every single step. And we will prove that given that, there is always a choice of vector in a decomposition of the identity, so that you can add that outer product of that vector to the matrix and move the upper barrier forward 2, the lower barrier forward a third, and still the barrier potential functions will remain less than 1. So this is exactly what we need to do our induction. And I should also mention this scaling factor is going to pop in here. So it's really not that I can always choose an outer product. I can always choose it times the scaling factor. I should tell you, because some people are rediscovering this in many different ways, if I only wanted to prove one of these identities, if I just wanted an upper bound on the eigenvalues or just a lower bound, then I wouldn't need the scaling factors. The scaling factors come from trying to satisfy 2 conditions at once, as I'll explain later. But there actually are interesting applications of this if you didn't have them. For example, like the Borgan-Safiri restricted invertibility theorem follows very, very simply from this sort of analysis because you don't need the scaling factors, but you only need a lower bound on the smallest eigenvalues. Yes? Yes. Well, no, actually, no. So the V's are going to be a decomposition of the identity. It doesn't change what it is because we scaled by the original matrix, the original Laplacian inverse. But right. Oh, V's. Oh, sorry.
You already collected some vectors.
Oh. Oh, no. We might reuse vectors. We might add a vector twice. So that's OK. It's just increasing its weight. So think of it, I'm doing sampling with replacement. Yeah. You would get a slightly stronger result. If you can prove that it's at least as good if you don't want to use a vector twice. But yeah, thankfully our decomposition, but the decomposition of the identity could change. There's no reason it can't. But in this proof, it won't. OK. So here's what happens. Then we just keep pushing forwards. And after, say, 6n steps, not only are all the eigenvalues between n and 13n, but after adding 6n vectors, but they all satisfy these barrier potential functions being less than 1. OK. So that is the main overview of the argument. I believe I have time to tell you a few details that will be useful for the future lectures. So the key statement here is just that I can always choose some vector from my set, appropriately scale it, and add it and move the barriers and keep my barrier potential functions less than 1. So let's see why. So we can understand what I'm going to do. Let me set at u prime my new upper barrier. So it's u plus 2. I'm shifting it by 2. What we need is that after I add the vector times the scaling factor at the new barrier, we need this potential function. We need to be able to control this. So here's an expression for it. Thankfully, this is the trace of a rank 1 update of a matrix, and there's a very simple formula for what that is called the Sherman-Morrison formula. So we get an expression for what this is, and it's a nice, easy thing to deal with. I will manipulate it and tell you what happens with it. What we're going to show is just it's at most what the value was initially. That's what we want anyway. And when you rearrange terms, the condition becomes very nice. You see that you can add the vector v with scaling factor s if and only if this inequality is true. So let me point out the important part of this inequality. There is a matrix in the middle that only depends upon A and the barriers. V does not appear in the middle of this expression. The vector v I want to add and the scaling factor s only appear on the outside. So what that means is I can rewrite it this way. I have what we'll call the upper barrier matrix U sub A. Is this matrix here. And the condition of whether or not I can add a vector v with a scaling factor is just whether or not this quadratic form is at most 1. And this makes sense. You sort of have an upper bound. Because the more, if I try to blow up this scaling factor more, s more, the largest eigenvalue will shoot up. And if I'm only moving the upper barrier forward 2, you know there's a limit to how much I can shoot up that largest eigenvalue, because I don't want it to cross the barrier. But the thing that's really important to us, well, there are two things. One, that this is a nice quadratic form in V. And two, this is actually turns out to be a very understandable formula, and I will explain exactly what these two terms mean in a little bit. You can do the same thing for the lower barrier. But here it's the other sort of condition. Here you can add a vector v times a scaling factor s if and only if you get a quadratic form that's at least 1. So this is because, again, the lower barrier, you want to push the eigenvalues away from the lower barrier, so you need to add at least some amount of that vector in order to move the barrier forwards. Now, what we need to do is we need to show that we can do both. We need to pick a vector v and a scaling factor s so that actually 1 sits between both of these quadratic forms. So here's what we know, and I will show you very simply in a minute, that we understand what the expectations of these quadratic forms are, which we can do because the vectors are a decomposition of the identity. I know that the expectation of the first quadratic form, in this case, is at most 3 over 2 times the number of vectors, 3 halves. And the value of the other quadratic form is at least 2 over n. So this is pretty good. In expectation, things are working out right. In expectation, this one is bigger than that one. So in particular, there does always exist a vector. Oh, by the way, I should tell you, before I put up this one, when I looked at this, we were actually stumped, I think, for about a week looking at these two expressions. Because if you have expressions like this, you always know that there is a vector, so that this is at least less than 3 halves m, and there is a vector, so this is at least 2 over m. But you don't always know there's a vector that satisfies both of these. When you have 2 expectations, you can't guarantee that. It turns out we don't need that. What we have is that there is always we have the one expectation is less than the other expectation. So there is always a vector e, so that the upper quadratic form is less than the lower quadratic form. This is where the scaling factor comes from, exactly. By trying to satisfy 2 inequalities at once, right? The expectations would have been fine. But once I have this, then I can find some number s to multiply them by, so that 1 is between these 2 numbers, given that they're both positive, which they are. OK, so that was I am not going to discuss the algorithmic problem now for not searching, but there is one at least. And then you can find the scaling factor. There have been some non-trivial things done with the algorithms for finding this, like using the fast multipole method. And actually doing it takes some interesting work. Doing the square, yeah. Oh, no, sorry. Oh, right, yes, you can, right. You can just substitute each of them. If you want to do it quickly, it's a problem. All right, I would like to do it faster than substituting each of them and checking. But yes, you're right. Algorithmically, so far, this is not a problem. There are only m vectors to check. But that's like, that gets me something like a cubic time algorithm, and I don't run those on big graphs, unfortunately. Right. Oh, I mean, just for the ease of demonstration. I'll show you the type bounds later in a moment. OK, so this tells us at least, oh yeah, so what I need to do is I'm going to show you a little bit about how we prove these inequalities, because it turns out to be very useful for tomorrow's lecture, at least the upper bound one. Oddly, it turns out to be very useful. So we actually came up with a couple of proofs. So let's say I want to bound the expectation. So the first thing to note is, of course, that, as many of you know, when you're taking traces, oops, yes, well, this really should have been a trace, but that's one real number when I evaluate the quadratic form. But you can rotate vectors and traces. So it's the same as multiplying UA by VV transpose. So I can understand exactly what the expected trace is, especially when you have a decomposition of the identity. The expected trace of a term like this is exactly, well, shuffling inside, you get the trace of UA times the expected matrix, which is I over M. So the expected trace for upper bound really is just the trace, I mean, not expected trace, the expected quadratic form value really just is the trace of the upper barrier function divided by M. So getting the expected quadratic form is easy. And now let me put back this expression that we had for what the upper barrier function is. Well, let me just look at its trace. There were two terms that I got out of Sherman-Morrison. The first one corresponds to the value of the upper barrier potential function of A at u prime where u prime is bigger than u. So that means that you're holding A and the eigenvalues fixed, and you move the barrier up. When you do that, the value of the potential function can only go down. So this turns out to be a very important property to me, as you'll see next lecture, that this barrier function is monotone decreasing in u. And that means that if I know by induction that the barrier at u is at most 1, then for every larger u prime, the barrier at u prime is at most 1. This is going to be one important fact we'll use about the barrier function. The other term turns out also to be very simple. The numerator that you see here is actually the derivative of the barrier function at u prime. So when the numerator here is the derivative of the terms, this function in the, I'm looking at the denominator, and you can prove the barrier function is convex. So not only is it monotone decreasing, it's convex. Well, that's actually pretty obvious for this barrier function. I'll show you other barrier functions on Wednesday for which it's less obvious. But once you know it's convex, then it is very easy to see that this term is at most 1 over u prime minus u. And that tells me that the trace of this matrix UA is at most 3 halves. So OK, we got lucky analyzing this expression, which, in most worlds should have been a nightmare. Really just came out to be lucky that it just came down to something about monotonicity and that we have some convexity in the term in the numerator as the derivative of the denominator. OK, I will say similarly, you can do the same thing for the lower barrier potential function. I put similarly in quotes because there's a little more algebra in this. It's not just a monotonicity and convexity type thing. But it's still only half a page, so it's not bad. OK, so that is what we needed to prove this lemma that says at every single step there is a vector in our collection that we can add. We can keep the potential functions less than 1 and move the barriers as I want. If you now of course, I made this a little loose, right? I made my, where did I put it? I made my lower barrier at 2, my upper barrier at 3 halves. If you tighten up all the terms, what do you get? We get that the ratio of the largest eigenvalue to the smallest eigenvalue, after I do this for dn steps, will be at most this ratio, this d plus 1 plus 2 root d divided by d plus 1 minus 2 root d. OK, I should say that I did this for dn steps. That corresponds to a graph of degree 2d, or average degree 2d. Because if you have a graph of degree d, that's dn over 2 edges. Each edge hits 2 vertices. So this is twice as many edges you'd have in a Ramanujan graph. And this ratio is actually just slightly better than the ratio that you get between the largest and smallest eigenvalues in Ramanujan graphs. So do just a little better with d at most twice what you get in the Ramanujan graphs. I do want to point out that this even works in the odd regime that I make d something like 10/9. So you actually can make d very close to 1. And then you have something like a tree plus a couple of edges. And you still get these bounds, and it still works. OK, so let me end with a few open questions. First, can we get Ramanujan sparsifiers? I asked this already, which is, can you get sparsifiers that approximate an arbitrary graph as well as Ramanujan graphs approximate the complete graph? OK, you're not going to get it from the techniques that I just gave you here, because you can't improve these bounds, at least asymptotically, that I gave you for sparsifying matrices. And you can see that just by plugging in random matrices or something like that. You won't improve that. So you're going to have to use something special about graphs. Actually, we do know some special things about graphs. I should have mentioned that here in this previous slide when I said I can make d very close to 1. If I do make d very close to 1, we can get bounds for graphs that are better than this. And it's exploiting something called low-stretch spanning trees. But we still don't really understand where the right trade-offs are there. But we know there are some special things for graphs. And there's a lot you can say about the vectors you get from graphs. I would really like to understand which of them are useful, because say low-stretch spanning trees we make by a completely non-algebraic construction. And can we get faster algorithms? So I told you there are people using things like the fast multipole method and getting algorithms that are close to time order n squared for building these sparsifiers, but you'd like something even faster. For example, if you want to make a decent expander, as Daron was in here earlier, I don't see him now. Oh, there, thank you, is proved. And you can just take a union of random Hamiltonian cycles. If I take d of them in the complete graph, right, that is a great expander with good probability. For me, a big question is, can you do anything like that? Any nice random construction that probably builds these for arbitrary graphs. Why am I so interested in this? Because I'm doing this for algorithmic purposes. Right? At least that was my initial motivation, of trying to solve systems of linear equations. And this algorithm is too slow to really be used for that. OK, so what's next? The next two, what? Yes? Oh, no, sorry. I shouldn't say, oh, right. Sorry, Hamiltonian cycles in the complete graph. You're right. In the actual graph, you couldn't use Hamiltonian cycle, because we can't build them. So you want to do a union of something random. We want some random sampling algorithm. I mean, OK, there's a random sampling algorithm where we can get n log n over epsilon squared edges quickly. But we want to do better. Yeah, so you want some simple random algorithm might do this. But I don't know what it is yet. OK, so in the next two lectures, we will exploit the mistake that I initially made. I sort of justified this whole analysis by looking at an expected characteristic polynomial. And bizarrely enough, that inspired the analysis we initially did. It had no rights to, we thought at first. But we now realize that when you have very nice distributions of polynomials, the expected characteristic polynomial actually tells you a lot about the existence of individual polynomials in the distributions that satisfy the same root bounds as the expected ones. So on Wednesday, we'll use this to give a positive solution to the Cadison-Singer problem, and on Thursday to get a very simple proof that there are Ramanujan graphs, or infinite families of Ramanujan graphs of every degree. Cool. Thanks.